So far we've only been considering one gas at a time. Now let's look at what happens when you have mixtures of gases. And this is called Dalton's law of partial pressures. So it turns out that if you were to look at the total pressure of a mixture of gases, it just equals the sum of the pressures of each gas individually. So whatever that gas would, whatever pressure it would exert if it were present alone. So the P total is just equal to P sub 1, P sub 2, P sub 3. Those just mean like gas 1, gas 2, gas 3. So whatever the pressures are of each one of those gases, add them all up and you get the total pressure. Another way to write that is, so if you wanted to calculate the partial pressure, so the pressure of just one of those gases, it's going to equal the moles of that one gas times RT over V. So R is a constant, the ideal gas constant. The temperature is not going to change as long as you have, each gas is going to be at the same temperature. You take the temperature of the mixture and it's the same temperature of all the little pieces. And the same with the volume. The volume is just the volume of the container. Each gas has the entire volume of the container to move around, and so they all have the same volume. So the RT over V is going to be the same for every gas in the mixture. The only thing that's going to change is the number of moles. So it's pretty much the pressure has to do with how many moles of each gas you have. So which moles do you use? It depends on what you're looking at. So if you're looking at gas 1, the partial pressure of gas 1 has to equal the moles of the gas 1 times RT over V. Or P2 is N2 times RT over V. Or if you're looking at P total, then you have to use the total moles, N total, times RT over V. But RT over V is going to be the same whether you're talking about, gas 1, gas 2, or all of them together. So really there's this relationship between pressure and moles that we're going to get back to in a little bit. We'll look at the mole fraction. But let's try to use this idea of partial pressures to answer this question. So you have a mixture of oxygen and methane. So you have 6 grams of oxygen, 9 grams of methane, and you put it in a 15-liter flask at 0 degrees Celsius, and they want to know what's the partial pressure of each gas. So I'm going to use the ideal gas equation here. So I'm going to have PV equals nRT, or I can solve that for N. So N is just going to be, I can. Right, first I have to solve for N. So I have to find the number of moles of gas. So they give me grams, and I want to find moles. So how do I go from grams to moles? Molar mass. So what else do they give me here? The volume. So volume is 15 liters. Temperature is 0 degrees Celsius, so I'm going to add 273 to that, so I get 273 is my Kelvin. R, 0.0821, you always have R, I'm going to give you R. Just make sure you have everything else in the right units. So PV equals nRT. If we're looking for P, then we have to know N somehow, so we're going to get, they give us grams, we're going to convert to moles by using the molar mass. So we have grams on the bottom, moles on top, so we have 0.188 moles of oxygen. And you have grams of methane to moles, so using the molar mass of methane, you get 0.563 moles of methane. So now I'm going to plug this into the ideal gas equation. If I'm looking for the partial pressure of oxygen, I want to use the moles of oxygen. If I'm looking for the partial pressure of methane, then I want to use the moles of methane. If I wanted to find the total pressure, I would use the total moles. So I find the partial pressure for each one of these. So just plug all that in and, go through this problem. You pause the video, you check the math, you do the same thing, so you practice doing it. We get our two partial pressures here, 0.281 and 0.841. And if they wanted now in part B, they're asking what's the total pressure? The total pressure is just the sum of the partial pressures. So total pressure is the pressure of the oxygen plus the pressure of the methane, and so I just add those together, and, I don't know what you get. When you add those together, I'm missing that number. I think you get 1.0 something. You work that out and we see what you get. Now, partial pressures and mole fractions, let's see how that works. Alright, so you're going to see this again when we talk about mole fraction. So the partial pressure of one gas divided by the total pressure, it's proportional to the moles of that one gas over the total moles. So pressure over total pressure is moles over total moles. where moles over total moles, this is called the mole fraction. When you look at moles of one piece over the total moles, that's called the mole fraction. So if you basically if you put it all together, you can get the partial pressure. So we have P1 over P total equals the mole fraction. So just multiply P total by the mole fraction, and you should get P1. So P1 is the mole fraction times P total. And we'll see this again when we talk about vapor pressure. So we'll look at mole fractions. And this example, they use mole fractions here. So they give you the mole fractions of each one. So mole fraction of carbon dioxide, mole fraction of oxygen and of argon. And then they ask, calculate the partial pressure of oxygen if they give you a total pressure. So they're asking with the partial pressure, they give us the total pressure, and they also give us the mole fraction up on top. So I just have to multiply the mole fraction by the total pressure, and I get the partial pressure of oxygen. You could find the partial pressure for any of these other gases the exact same way. They just asked about oxygen in this one. So if the atmosphere is to be held in a 121 liter space, so that's your volume, at 295 K, that's your temperature, and they want you to find moles of oxygen. Moles of oxygen. All right, well, do I already know the pressure of oxygen from up here? I know the pressure of oxygen. So I was able to find the partial pressure of oxygen. I have volume, temperature, I always have R. Pressure, I have to convert that to atmospheres. So I'm going to convert that to atmospheres. I have 131 torr. 760 torr is 1 atmosphere, so I'm able to get to atmospheres pretty easily. And now I have PV, T, and R, and I just want to solve for N. So I'm going to plug that into my PV equals nRT equation. Solve for N over here. And you should check this too, make sure you can rearrange that equation. All I did was divide by RT on both sides. So I get PV over RT is N, and I got 0.879 moles of oxygen. Alright, so you go through that problem again. Another application of when you have a mixture of gases is whenever you're collecting something over water. So in this process you have a reaction going on in here, and you're creating some oxygen gas, and you want to collect that oxygen gas. What you can do is you have this set up like this. You have your reaction in a test tube, and then you have it kind of sealed off. You have another tube that goes right into a flask or a beaker that's upside down and filled with water. And then what's going to happen is the gas that you're making is going to bubble through the water, and it's going to replace this water. So water is going to leave, and you're going to collect your gas over water here. But when you start doing that, there's going to be not just the gas that you're collecting, but because you're collecting it over water, there'll be some water vapor, there'll be some water gas in there as well. And so when you're measuring the total pressure is going to be the sum of those gases. It's going to be the pressure of whatever gas you're collecting plus the pressure of water, the vapor pressure of water. And it turns out the vapor pressure of water is going to change at different temperatures, but it's a known value at any given temperature. You can just look that up in a table. So usually you'll measure the total pressure, and then you'll know the vapor pressure of the water, and so then you have to solve for the pressure of the gas. So you just subtract from the total pressure the pressure of water, and that will give you the pressure of the gas. So this next problem is a collection over water problem. So you have that reaction, the potassium chlorate, so that was in the picture above. So when a sample of potassium chloride is partially decomposed in the setup shown above, the volume of gas is collected. Okay, so that's 0.250 liters at 26 degrees Celsius and 765 torr. That's your total pressure. This is the total pressure. So that's the pressure of the oxygen gas plus the water. And then they tell you the vapor pressure of water at that temperature is just 25 torr. And then they're asking about the moles of oxygen. How many moles of oxygen are collected? Alright, so I'm going to use PV equals nRT to solve for N, the number of moles. So I have volume, I have temperature, I have all these pressures. How do I find the pressure of oxygen? I have the total pressure and I have the pressure of water, but what I really want is the pressure of oxygen because I'm trying to find the moles of oxygen. So remember, my P has to match the N. So I'm going to first solve for the pressure of oxygen. I take the total pressure here, this is 765, that's your total pressure. Subtract from that the vapor pressure of water, and this will give me the partial pressure of my oxygen in torr. I don't like torr, so I have to do a unit conversion over there. So 760 torrs 1 atmosphere, so I can get to the partial pressure of oxygen here is 0.974. So now I have P, V equals nRT. So I have P, V, R, and T. I'm just going to solve for the moles of oxygen. Just make sure when you're using this now, if you have a mixture of gases, the pressure that you're using has to match the moles. So if I'm looking at the pressure of oxygen, then I have moles of oxygen over here. If I had the total pressure here, then I need the total moles over here. But all they're asking for is for the moles of oxygen. So I'm good here. So that's why I use the partial pressure of oxygen. Alright, so I just solved this equation out. I should get 9.92 times 10 to the negative 3 moles of oxygen.